Welcome everybody to day one of lecture for the OSG virtual school pilot in 2020. You got an overview of the school yesterday and an introduction to the concepts of high throughput computing. Today, I'm going to go into some detail about how to execute high throughput computing tasks using the HTCondor compute scheduler, which is a really critical component of not just the Open Science Grid, but is used widely for scheduling high throughput computing and in a way that makes it easy to manage lots and lots of independent tasks for the user. So we'll talk briefly about how the HTCondor job scheduler works at a high level, including what it's doing across, say, a high throughput computing cluster in order to execute your jobs and the jobs of other users across those. We'll talk about the logistics and semantics of submitting, running, monitoring, and reviewing jobs. We'll talk also about the best ways to submit multiple jobs after starting with what is sort of a simple single job example for the logistics. And then we'll talk about testing, tuning, and troubleshooting. And I'll mention that what we cover here are sort of the basics of using HTCondor. There are a lot more features, including some and bonus exercises that you might be interested in. And this presentation comes from a longer version with more detail that we deliver at HTCondor Week every year. So if any of you are interested in those resources, you can look for them online or ask us where they are. But if you look for Condor Week 2019, you'll see that one of the first presentations in the schedule is an introduction to job execution. So as a reminder, you have access to and will be executing exercises today on our local high throughput computing system at UW-Madison Center for High Throughput Computing. This is our research computing center at UW-Madison that supports research all over campus and partners with other entities on campus that may support computing or data resources for research. We have a large Condor pool that supports really any computation that fits on a single server as individual jobs. So these can be lots of single core jobs, these can be one or more GPU jobs or high memory jobs. And it's that system that also backfills our relatively smaller cluster that's just for multi-server MPI. We're here to learn high throughput computing, so that's why you have access to our high throughput computing system for the next year. And that gives you sort of a consistent environment for testing out Condor. And then starting tomorrow, you'll actually be running on the Open Science Grid. But CHTC has a longer history beyond our role as the Research Computing Center at UW-Madison. In particular, we are the pioneers of the ideas of high throughput computing that have grown alongside the development of the HTCondor compute scheduler, which is oriented toward and enables high throughput computing at scale, and even across clusters that are distributed, like what we see in the Open Science Grid. Condor was developed since the 80s, or has been developed since the 80s at UW-Madison in what is now known as the CHTC. And it's used all over the world by research institutions, companies, and it's the basis of the entire Open Science Grid. You'll learn a little bit more about how Condor makes the Open Science Grid work tomorrow. Today, you'll learn how it works for users and how to make use of it yourself. And Maron Livni, who is a professor in computer sciences, this is sort of his contribution to the world, defining the paradigm of high throughput computing and continuous contribution to Condor and the Open Science Grid, for which he leads all of those projects. So let's talk about Condor and how it works. The basics are that you, the user, can describe many computational tasks at a submission point that you log into. This is typically a server that is a submission server, submit point. You may even hear us use the term node, though we'll try to use the term server. And you communicate those to Condor, which is then keeping track of what we call execute servers, or you may hear us call them executes. And it matches jobs to the execute nodes according to fair share policies and other configuration of a Condor pool or cluster, really. Let's talk about what a job means. So we discussed yesterday that high throughput computing is the idea of breaking up a larger task into smaller, completely independent tasks. A job in our scenario, as it is defined on most other cluster environments, is a unit of computing that can be independently scheduled and executed, that doesn't need to be directly interacting with others or co-scheduled with them. And you'll learn later in the school in one of the bonus topics, if you want, about how to set up multi-step workflows where some jobs run before others, but each job is still an independently schedulable unit of computing work. And what defines a job, other than the fact that it's independent, is that it has an executable, a script or program, or maybe a script that runs multiple programs that take some form of input. These may be files or options, like command line arguments, and produces output. So this would be any files or even information printed typically to the screen or the terminal that is produced by the executable based upon the input that it gets. And in order to run many jobs, in a cluster environment, typically, the executable must be able to run on the command line without any graphical input from the user, so no point-and-click interfaces necessary, and otherwise no input from the user while it's running. In order to automate things on a cluster, you want jobs that can run completely on their own, just given the executable and input. Now in Condor, because Condor schedules not just whole servers, but portions of servers, we have the idea of a machine. And if you peruse the Condor at any time, you may see this term. It refers to a whole computer, a desktop or a server that has multiple processors, some amount of memory, and some amount of file space that's available to run jobs. A slot is an assignable unit of the machine, or a portion of the machine, as Condor is configured to break up machines. So this will be a portion of the cores, maybe one or more, some of the memory and some of the on a machine if there are multiple slots. A machine will typically have multiple slots, and Condor can be configured to break up a machine into predetermined static slots, or can be configured to sort of dynamically reshape and size slots based upon what jobs look like. And that's generally how Condor is configured. It's how we use it in the CHTC. So let's grow our definition or idea understanding of how Condor works. I mentioned that there's a submit server, there are execute servers. Typically in a large cluster, there's a separate machine called a central manager, and this is really the matching brain. It's continually getting information about what jobs want to run and what resources they need, or if they have special requirements about the server other than the resources, like it needs to have a GPU of this type. And then it's also gathering information from the execute servers about what types of resources they have. And then it matches jobs to machines and matches jobs to slots by working with the execute servers to break themselves up into slots and reconfigure themselves as some jobs finish. After it makes that match from jobs to slots, then the submit server and the execute servers communicate directly to each other. And once a job finishes, the execute servers report back to the central manager, which is otherwise continuously, again, looking at information from all the execute servers and all the submit servers. There can be more than one to match jobs to slots. Condor is typically configured this way in a large-scale system, like how we're going to use it. But the same paradigm can work on a single computer, where the queue, or sort of the parts that are on the submit server, is on that computer, but the other processors can be designated as available slots for computing. And the central manager in that case is pretty light. It doesn't have to think so hard about just the cores on a single server. So Condor is sometimes used to scavenge resources on pools of desktops and make those into a virtual cluster. So let's talk about what job submission looks like for you, the user. We've already discussed that jobs have executables, input and output. Here's sort of a conceptual diagram. We might have two input files. Let's say we're comparing data from each state. This particular job is going to compare Wisconsin against US averages. And it's going to compare those and then produce output that in this case would be specific to the Wisconsin input that it got. So we've got one unique file, one file that might be common across multiple jobs. And then the command that we might run this in our hypothetical example would be, the program, which is the first item in our command, the executable, the names of the input files in order, and what we want it to name the output file that it produces. So let's translate that into a basic submit file. And there are multiple components here. We'll walk through them each one at a time. First, or not first, it doesn't really matter what order these in, but first we'll talk about the executable. So the executable that needs to go with each job we'll list here. This can be, in this case, compare states might be a compiled binary that contains everything it needs, but it could also be a script that runs some other programs, perhaps. In our case, it's a single executable. Here are the arguments. So we break out between the executable and the arguments, and Condor will use that to run this command for us after it has matched our job to a slot. Before it runs the executable and that command, it will transfer files, and it'll only transfer the files we tell it to. So it's important that we list our input, and if there was any other software that needed to go along with our job, we'd list that here too. Even though we don't think of that as input data, it's still sort of input in terms of being necessary ingredients for our main executable to do what it needs to do. Importantly, we don't have to list the output file. When output is created during a job, it will automatically be transferred back. And I'll show you a schematic of how that plays out in the logistics of what happens at various stages of Condor editing your job. There are other files that Condor can create for you if you ask it to, and we highly recommend that you use these in all cases. A log file is a log that Condor will create and that exists on the submit server the whole time your job is running, where it will list the different logistic steps it's taking to run your job. And we'll see what that looks like later. We'll see a log file. It can be a good place to look for any issues or reasons why your jobs might be taking longer than you think they should. We'll explain that later. And then you can also ask Condor to capture what's called the standard output or standard error from your program. Whether you realize it or not, if you've run programs on the command line or even in like a MATLAB terminal, you'll typically see output back to the screen or the terminal. And that is usually what we call standard output. You can imagine that if Condor is running your job on an execute server and you're not there to see that, which is kind of the ideal, that Condor can do this without you, you might want it to capture that. And so standard out is where it would capture output that's produced by your executable. Standard error would be a separate file to capture error information. And traditionally, programs report different information to standard out versus standard error. That will be decided by your executable, but Condor can get both of those types of information. And then this last chunk is where we will request, on a per job basis, we need one CPU or one core, 20 megabytes of disk, and in this case, 20 megabytes of memory. And we'll talk a little bit later about how to tune and ensure that you're requesting enough for your jobs and why it's important to actually tune that. And then this last line, Q, we can say Q by itself or Q1 means that we're submitting one job. And so we'll see what it looks like to submit one job, and then we'll talk about how to queue multiple jobs in the submit file. So let's submit this example job and kind of see how things go. How do we monitor the job as it's running? What tools does Condor give us, and how do we use them? So to submit jobs, first, we'll learn the command condor submit or condor underscore submit, which we will give as a first argument the name of the submit file. So here's that example, condor underscore submit, job.submit. And you'll notice that there's a convention with Condor commands. They're always condor underscore something, where the something is hopefully semantically meaningful in English in terms of telling you what that command does so that they're easy to remember. So if we were to submit this job, what we would see back is a message from Condor to the standard out, since it's the terminal. Submitting jobs, one job was submitted to cluster, in this case 128. That cluster is referring to this set of jobs or this submission of jobs. So this is the 128th submission of jobs to this queue. So there may be others that have been submitted by other users. It's not referring to like the number or name of our compute cluster, but really sort of a cluster of jobs. And we have one job in this cluster. If we run condor underscore queue, that will show us the queue, but just the information for our own jobs. So by default, condor queue shows you just your jobs. And it's going to do so in a way that it would be batching up jobs if we had submitted multiple of them. So we'll see when these jobs were submitted, how many are done, how many are running, how many are idle. In this case, we only have one total job, and its job ID, so there's one number listed here, is 128, the cluster number, .0. Let's talk about what that means. That 128, again, is our cluster number, but each job has a unique job ID that includes another number. So the first job in a set that we've submitted with one submit file will have a process number, a process ID of 0, and then those will increase if we had submitted multiple jobs. So they increase by integer values, 0, 1, 2, etc. So we would see a range of job IDs if we had submitted multiple jobs. Also, when you run CondorQ, like by itself, it shows you just your jobs in this batch mode, but you can request to see jobs by the username, by the cluster ID, so you could view just one set of your jobs instead of all of them at once, or you can even view jobs by just a specific job ID, so including that .0 in our case, 128.0, if we wanted to view just this single job. And there are other commands that use this convention where you have the option of specifying the command for viewing all jobs of a user, just of a cluster, or just of a particular job. And so that will be denoted with this UCG to indicate that you have those options with the command. A little more about CondorQ. You can view a batch of jobs with more information per each job by using this no batch option. So that will kind of unbatch the output from CondorQ. And here's what that looks like. If we had submitted more than one job, what we would see is the job ID at the left increasing, information about who submitted it when, how long it's spent running. That would be 0 time at this point before our jobs have matched. The status column will be I for idle, R for running. So those are informing us which columns of the previous CondorQ batched output each of these jobs is in at the moment. The relative priority of the jobs, which we won't talk about here, but you can look into if you'd like to indicate that some jobs should run before others. And the size would be the memory used, and then the executable that's running. So you've got a little more detail with no batch. And we'll use no batch in the following slides to show you in detail what steps our test job is going through. So here's CondorQ no batch. Here's that same output. We're just seeing it for this 128.0 job. And once we've submitted our jobs, here's what we would see back on the submit server. We had already created these files. These are ingredients for our job, including the submit file that needed to exist before we submitted. But after we've submitted, Condor will immediately create that log file and start writing information to it about what steps it's taking to match and run our job. And it will also create placeholders for the standard out and standard error files, partially just to make sure that those files can be created and that all of those logistics will work out fine. But we won't get that information, and these files won't have contents until the end. Once our job is matched, it will begin transferring files. And if you happen to catch that in the queue, you'll notice it as this symbol for input that's common at the command line. And that means that Condor is transferring over our executable and any files that we listed in the transfer input files line of our submit file. So it always by default transfers the executable, but it will transfer any other files we tell it to. And it's going to add those to a temporary execute directory that it's creating. We won't know the name of that directory. It's created on the fly so that Condor can clean it up when we're done. But it's sort of like the little playground space that our job has to use on the execute server. So after it's transferred those files over, it will start running our executable. And we'll see this in the queue with the status R. If you were to go and connect to that job, you could see that there would be files that are generically named to capture our standard error and standard output. That information will get renamed when it gets transferred back to the submit server. And our job may also be at that point already writing output data. When our executable finishes, Condor will automatically transfer back that standard error and standard output data renamed to the file names that we chose. It will transfer back any new files that have shown up in the top level of our execute directory, but it will ignore subdirectories by default. And this is useful because this is where you could put data that you know you don't need at the end, but that your job may be creating in an intermediate sense that it may need while it's running. So this is one way to control which output comes back. And when the job completes, we'll have all that information back on the submit server. Our job will have left the queue, and so we'll no longer see it in the queue. There's information at the end of this presentation about how to view old jobs with the command condor history. So if you're interested in that, you can go see it, but we won't cover it here just for time's sake. So there are sort of three major states that jobs can go into. After you've submitted a job, it goes into the idle state. Before it starts running, it's transferring files. These are events that are logged in the Condor log. And then after your executable completes, with or without error, Condor will transfer back any output that is shown up in the top level of the execute directory. And the job only briefly exists in this completed state, as Condor is doing some final logging before it leaves the queue. So you may not ever see jobs in this completed state. Here's what a log file might include, and there would be more information than what I've shown here, because logs can get a little longer than what we'd like to fit on a slide. But there will be an entry with a timestamp for when the job was submitted and from what server IP address, if you care about that. Here's the job ID number here, 128.000. You can have more jobs than 1,000, but this is sort of the default format of the logging information. We'll have similar items for when the job started executing, when it terminated. And what's really important down here at the bottom is that Condor will give you a table of which partitionable resources, so which resources on the machines were given to your job in the slot assigned to you. So that's what was allocated versus what you requested and what you used. And you'll notice here that my job only used 14 kilobytes of disk space. I must have had relatively small files, and 1 megabyte of memory, again, probably because those files are relatively small. But I had requested 20 megabytes of disk and 20 megabytes of memory, which were obviously way more than I needed. You'll notice that I was given a lot more disk space, probably just because the server had a ton laying around that could be allocated to my slot. But still, I could have been requesting less. And it's important to tune the resources that you request because, again, you're always only running on a portion of a machine on a single slot, not the whole thing. And a machine can have as many slots as it has CPU cores. Some of the slots in CHTC or in the open science grid, or some of the machines, sorry, might have tens of cores. In CHTC, we have some servers with 80 cores. And ideally then, there would be enough memory and disk for all of those cores to be available in separate slots. So if you are over requesting memory or disk, you are blocking your jobs and the jobs of others from being able to use that memory or disk, and you're matching to fewer slots. There may be more machines that would have enough memory and disk for your jobs if you weren't requesting too much. Conversely, if you request too little and your jobs attempt to use more memory or disk than was given to you in your slot, Condor can hold your jobs so that you're not negatively impacting the other jobs on the server. And we'll talk about job holds in the testing and troubleshooting section and how to handle those. But back to resource requests, this becomes really important. In any high throughput computing system, typically you can game that system by letting your jobs, if they're small, fill in all of the excess spots that other people's jobs don't fit into quite as well. And in the open science grid, remember that we've got this table that I showed you yesterday, where this ideal category is kind of what you're aiming for. So again, if your jobs are requesting more memory, more disk, especially in the open science grid, that can significantly reduce the number of slots available to you and therefore the amount of throughput you can get. So only request what you need. Make sure to pay attention to those numbers in the log files when running, say, a small number of test jobs before you submit a really large batch of jobs so that they are optimized to get as much throughput as possible. So let's talk about submitting multiple jobs now. We want to go from one job to being able to submit multiple jobs. So over here, I've got a snippet of a submit file. I've left out the request memory and disk because they're less relevant to how we would submit multiple jobs, right? Those are per job requirements. So even in a single submit file that's submitting multiple jobs, those resource requests are per job. But let's say we had started out with a different scenario. We've got an executable that's going to analyze an input file and produce an output file. So we know we need to transfer that input file. We know that we want log, output, and error files for each job, but let's say we've got multiple input files. How do we communicate that in the submit file if we've got multiple input files and not just one? Well, one option that you could technically do would be to create a bunch of different submit files that each queue one job and to manually create those and insert the file name with this 0 and 1 and 2 variation. But let's say we had many more of these jobs. That's a lot of scripting. Condor has some things that makes this easier for you. So if your jobs differ by these integer-based numbers in your file names, Condor will actually let you use the process ID of those jobs, right, which starts at 0 and goes up 1, 2, 3, etc. You can use that within the submit file. In fact, you can also use the cluster number such that you could identify these jobs, say, in the error and output and log files, according to which set or which submission they belonged to. That way, if you had multiple submissions going of related jobs, you could distinguish those files. So you can do that within the submit file by using variables for cluster and process. You could also use cluster ID or proc ID. Those are interchangeable. Here's what that would look like, and I'll kind of walk you through this. So this is the same submit file we just saw before, but instead of saying file.in, now we can say file $process.in, file $process.out, and for each job that we submit, the process value that gets assigned by Condor will be inserted into these arguments and into the file name that needs to be transferred. So when we queue 3 jobs, this submit file will get submitted effectively once, where the process value is 0, a second time where the process value is 1, a third where the process value is 2, and so on. And we can also use the cluster value. In fact, we could have used the cluster value and the process value in the same file name. But in this case, we might have one log file to capture all of the logging information across all of our jobs if we didn't want a separate log file per job. But with output and error, of course, we'd want those to be separate files, or else they would get overwritten when each job finishes. So we can put the process numbers there too. So all of these jobs will belong to the same cluster. They'll each have a unique process number, and that's how we've submitted multiple jobs. Is there a question? I just heard a chat. Okay, great. And if there are questions, you can interrupt me. We will edit those out even though we're recording. All right, so that's sort of one basic way of submitting multiple jobs. We'll talk about how to submit multiple jobs if they're not numbered. But first, let's talk a little bit about organizing jobs and job files. So you might have lots of input files, lots of output files. Therefore, you'll have lots of error files, log files, and Condor also gives you tools that help you to organize these the way you want to back on the submit server. So let's say that we've got the same scenario. We're already using $process in the submit file, but let's say that we'd like to organize our input files into a separate folder from our log files and our error files. Some of our users really like this organization scheme. Everything else in the submit file would look the same, except that we can place our input files into this folder ahead of time, create these log and error folders ahead of time, and then tell Condor, rather than transferring the input file from the top level of my submission directory next to, say, my submit file, transfer it from a folder called input, and then here's the file name. So we can give the path of the file where it is on the submit server, and Condor will just look for it and grab it from there when it makes the transfer happen for each job. Similarly, we can tell it to write our log and error files to different directories when that information comes back. And again, since these files are created as placeholders when the job is submitted, you can even verify this at the time of submission. So that's what that would look like. Here's what happens. So remember that each job will be specific to its process number in this particular case. When Condor goes to transfer files to a slot that it has matched our job to, say it's job 0, it will copy over the executable, which it always expects to be in the submission directory where we typed Condor submit. But now it knows to grab our input file from this input folder. The fun thing is that regardless of how you have things organized on the submit server, Condor will transfer all of the files into the top level of the execute directory. So our executable still needs to expect that this file is in the same location, But the advantage is that we could change up how we're organizing these files and change our submit file accordingly, and our executable won't have to change or know how we had things organized back here. So it keeps things really simple. And again, our output created here would get transferred back to wherever we've told Condor to store that. Typically by default, output files get transferred back to the submission directory. All right. What if you wanted a different folder for each job? So say we have multiple jobs, and instead of separating out files by their type, we wanted to have a different folder for each job. Looking up top here, one of the advantages that might give us is that we could name all of our files the same thing for each job, but just have a differently numbered directory. And you can accomplish this with a feature in Condor called InitialDir. And this sets the relative location for all files other than the executable. Condor expects that the executable will always be in the submission directory where you type Condor submit. But with InitialDir, it will treat all other files, both input that it's going to transfer and logging and output and error files that it creates. It will create those or expect them to be relative to what we've set as the initial directory. So in this case, we could use $process to correspond to the numbering of different directories we've created. And then all of our file names are just consistent across all three of these jobs. And another note, the directories must be created before the jobs are created. Otherwise, Condor sort of presumes that there must be an issue on your part, that maybe you're referring to a location that doesn't actually exist and that it's not supposed to write to. So what about non-numbered jobs? I promised you that we'd get here, and this is what actually most people's scenarios are, and there are some really neat tools in Condor that help us with this, so that you don't have this scenario of needing to write a different submit file for each state that you want to compare, if we're thinking back to our compare states example from the very beginning. Let's look at that. So I already mentioned that it is possible to script the creation of many submit files where each one queues a different job. So you've got multiple queue statements to be dealing with. That's not recommended because it's tedious, it adds a lot of extra effort for you. And Condor has great tools that are probably very applicable to what you'd like to accomplish. And there are 3 options of different queue statements that you can provide that will allow you to create and then reference your own variables. So just like we used cluster and process before, those are Condor's native variables, you can create your own variables and communicate to Condor what's different about each job based upon the values for those variables. So one of the first ones that's pretty straightforward is that you can queue a variable matching all entities in your submission directory that match a particular pattern with a wildcard. A wildcard means that it would be any file named something.dat, although it would match directories too in this case. And we're just calling this state because we're comparing states. We get to name our own variable. Similarly, we could say, well, actually, let's make that the directory name. We get to decide what this variable is. We've happened to call it directory. It doesn't have to be directory. We could say matching job asterisk, meaning for every job directory we've created, like job 0, job 1, job 2, or job apple, job banana, job carrot, use the name of that matching entity wherever I have $directory as a variable in my submit file. You can put the list of various values into the submit file by saying queue variable in, and then providing those values in parentheses. Those can also be listed in subsequent lines of the submit file. The Condor manual talks about that. But the option that we recommend the most is this last one, queue a variable from a list, where then you can provide the list of different values in a separate file. We recommend this for several reasons, so I'll work from the bottom here. First, the queue from feature supports multiple variables. So we could say queue variable 1, variable 2, and then in that separate file, have it be a comma-separated list of values where each row or each line of that file represents a different job and can have 2 or more, really 1 or more variables, variable values to populate into the submit file. We like this one because it's highly modular. You can reuse the same submit file and just change up that external list of variables. So it's really great for submitting multiple batches, like doing a test of just a few jobs first with a short list of of job combinations of variables, and then creating a longer list file when you're ready to submit a larger submission. There is an additional file needed, but you can typically automate that. If you have one variable, you can run an ls command and create that file. And many of our staff can help you sort of quickly create this external list file. But it also creates a hard copy of what you did because you had that file, so it's very reproducible. It's easy to know what you did. Versus the matching, since it matches files or directories that happen to exist in your submission directory, doesn't really give you a hard copy of exactly what set of tasks was done. So it's a little less reproducible. And then defining your variable values within the submit file is reproducible, but it's a little harder to automate the creation of that information within the submit file for most people. So that's why QFrom is our most popular. And we've got exercises for these that you can try out. So let's last talk about testing and troubleshooting. And we'll talk about what types of things can go wrong from Condor's perspective and what information is available to help you with testing and troubleshooting, as well as some other Condor tools. So there are two sort of categories of ways that jobs can go wrong. One is that jobs can go wrong internally. This means that your executable experiences an error. It can't make sense of the input, it has a bug. This is clearly something you need to fix, but it's internal to the executable. When executables fail, they typically give some indication of that failure to the operating system, and Condor can intercept that and reflect it back to you. But it's also typically information that's going to be captured in the standard error, standard output of your job, which Condor otherwise kind of has no purview of except for capturing it and moving it back to the submit server so you can see it. But the other category of ways that that jobs can go wrong is that they can go wrong logistically, meaning that there's something about your job request that Condor can't honor. And this is usually something that you need to fix in the submit file rather than in the executable, or that maybe an admin might need to help you fix if it's, a reason Condor can't run your job because there was something wrong with the execute server. That's generally much more rare. But some common reasons are that like a job can't be matched, the requirements in your job don't happen to match anywhere in your cluster, or that it's just taking too long because there aren't very many of machines that can make slots for your request. Your job can go wrong in that files that you told it to transfer don't actually exist, or you had a typo in your submit file when you told Condor that they needed to be transferred. Things like your job used too much memory or disk, or even that Condor couldn't even start your executable because it was poorly formatted to run, say, in a Linux cluster like CHTC. So first, your first indications that something might have gone wrong, right, are if your jobs have completed, they've left the queue, but you don't have the output you're expecting, or that output doesn't have all the data that you're expecting. And so there are various places you can look. The log file, again, will have information about the steps that Condor took. There may be, in rare situations, indications that Condor couldn't take some of those steps. Like your job was interrupted and so had to restart. That would be maybe an explanation why your job took longer than it needed to. But the log file also record an exit status reported from your main executable if one was given. And if that's non-zero, that tells you that something else was wrong with your executable itself. It exited with an error indication. And then beyond the output files, which you've probably already noticed are wrong, the standard out file may have information from your executable that talks about why it ran into an error, and therefore gives you information about how to fix that with respect to the executable, or say if there was an issue with your input contents. Standard error, again, will capture errors from the operating system or reported by the executable itself. So those may be very specific, or you may need help from whoever supports your cluster in making sense of some of those too. So even though they're from your executable, typically the staff that support your cluster might be able to help you make sense of the information from these. So most of these are referring to errors within your executable, that first category. If Condor cannot honor some aspect of your job submission description, it will generally place your job on hold. And this is to bring the issue to your attention in the queue. So it's a different state in the queue besides the idle and running states that we've already discussed. And Condor will assign to that job then a hold reason that you can view in the queue. A job that goes on hold is interrupted by Condor. So say your job is using way too much memory. Condor might put your job on hold for that reason. It has to do so in a way where all progress is lost because it needs to keep your job from causing any more potential issues on that execute server. So you won't have the ability to look at any output, but your job will stay in the queue in the hold state until you remove it, or you can fix and release it. And we'll see that in just a couple more slides. For diagnosing holds, you can view that hold reason in the log file with condor q-hold, which you could give a specific job ID, but if you do that without the job ID, it'll tell you about all your jobs, including their hold reason. Or you can view just the hold reasons without any other information from the queue by doing condor q-hold, so tell me just about my held jobs, and then auto format just the hold reason. And so in this case, here are some sort of common examples of hold reasons. So job has gone over the memory limit of 2 gigabytes in this case, or 2,000 megabytes. Here's you told Condor to transfer this Python script as part of your job, but it didn't exist there. So maybe you have the file path wrong or the name of the file wrong in the submit file. Or it's trying to transfer an error file back, some of your output back to the submit server, but your quota on the submit node has been exceeded because you were only given so much space by the administrator. So here are some other common hold reasons. I'll leave these here as reference. In CHTC, it might include something like our local policy that jobs by default only get to run for 72 hours. And so maybe then you need to talk to the people that support your cluster and see how to be able to run longer jobs if possible. And maybe they'll direct you to break them up further in a high throughput way. But your job can also be put on hold just because it's causing some other problems, and the admin wants to keep your jobs from creating any more of those problems too. So, but in any case, you'll have an informative hold reason that will help you figure out what to do next, either on your own or with help. If jobs are held, or even if you know they're wrong and you want to hold them yourself, you can do so. So if the issue is that your job's already held and you need to resubmit it, so you need to fix something in the submit file, remove the jobs first with condor_remove. There's an exercise on this. And then you can resubmit. If the problem is within the executable or the input file, so the submit file is correct, but the problem is like a bug in your executable, you could leave the jobs in the queue, fix that executable bug, so just replace the executable file exactly where it's supposed to be on the submit server, and then release the jobs. So you could first hold them yourself, even if you know that that's a problem and you want to hold all of your jobs, you can do that, all the jobs of the same user or cluster, and then release those jobs, which puts them back into idle so they can run again. There are links in the Condor manual that talk about these things.